Thank you so much for coming here. Awesome to see everybody here. Really excited to talk a little bit about cloud storage, mostly object storage, I'll confess, and AI applications. So let's dive in. My name is Vamshi Kamneni, by the way. I'm the product manager for Azure Object Storage and our data management services partner ecosystem. It's great to be back here after many years. So yeah, we'll dive in. What we'll talk about today is a little bit about how we got here. Object storage is not typically what you think of when you think of AI or other workloads. So, we'll talk a little bit about what workloads, kind of how things have evolved over the last few years, especially I would say over the last 5 to 10 years. We'll talk about the different storage requirements for the AI workloads. And then we'll dive in and spend a bunch of time with my colleague Saurabh here on RAG, the RAG pattern, and how object storage is used in conjunction with vector databases. You hear about RAG, you hear all about vector databases, but there's always a hidden kind of sub-layer of storage doing its job, like always, under the covers. Let me go back here. And then we'll talk about, and we'll wrap up with talking about what might come in the future, right? And talk about things like, Andrej, Karpathy talking about the LLM OS and all. So let's dive in. So let's talk about what object storage has looked like over the years and how it's evolved. And I'll go back where maybe folks don't typically go back, which is to the mid-90s. I don't know how many of you folks know this paper called Ocean Store by folks from Berkeley. There's a couple of folks. Okay, actually, yeah, that's awesome. I was not sure if there was going to be anybody up. So Berkeley, wonderful systems university over many, many, many decades. They wrote this paper, I think mid-90s, late 90s, called Ocean Store. That paper was way ahead of its time. I consider it sort of the ancestor or grandfather or whatever of all the object storage systems that came after. It was, even now, I was actually reading through the paper yesterday after many years, probably a decade after I last read it. And it's still amazing how many concepts from that paper from one of the Berkeley systems teams, made it into S3, made it into our service, Azure Blob Storage, GCS. So it really was one of the first places to talk about distributed hash tables and all of the things that underlie today's modern object storage systems. There are also other systems, sort of precursors. One of them that many of you may recognize is content addressable storage. Centera was sort of the canonical example of this back in the day, providing archival storage and things like that. But it wasn't really until sort of obviously the mid-2000s and you have S3 launching that just kind of really kicked off the modern era. Obviously you had Ceph and you had SwiftStack. But in this time, it was still very much either backup and archive storage or cloud native application storage, where the cloud applications were really expected to know what they were dealing with. Simple key value store, latency wasn't something you could really count on, and certainly consistency wasn't something you could count on, right? Like the original object store systems were often weakly consistent, not strongly consistent, no read after write consistency. So it actually kind of limited what they could be used for, but there's no question, again, that really, I would say, full credit to them, AWS and S3 really kind of started this era of object storage being used for everything. Things kind of evolved, and by the time you get into sort of the mid-2015s, I would say, at least all the cloud hyperscalers had relatively mature or maturing object storage services. And what started changing by, I would say somewhere 2015, 2016 is, for those of you who remember the buzzwords of a decade ago, it was all about big data and, analytics and big, and again, the reality of big data took many years after the buzzwords came out. But what changed fundamentally for object storage at the time was we started seeing a lot more throughput requests on our data, right? Like up until then, you had data which, by and large was very cold, right? You could look at the IOPS per terabyte of data. It was very, very low. Again, P99 latencies and things like that were typically measured in the seconds. Not really something that was in the main line. I think analytics was the first time that you really saw this happen. The other thing that started happening in that time period is customers who were already using it for applications started relying on these applications as mission critical applications more and more. More enterprises were moving their apps and those who were rewriting and saying, hey, this needs to work the way I'm used to my storage systems on premises working. The big thing for that was strong consistency. For those of you who remember, S3 didn't have strong consistency for a very long time, until fairly recently, actually. And that was, for a long time, the differentiator for our service. Azure Blob Storage had been strongly consistent since the beginning due to some design decisions we'd made way back in 2007, 2008. So these two kind of trends were happening. The throughput growth and then integration with analytics engines. Initially it was Hadoop, and then it was sort of Spark, and then you have, of course, Databricks and Snowflake. Nowadays you look at these systems, it's much more, you're more likely to see a Databricks cluster or a Snowflake cluster having these analytics things. This was around the time that we started going, hey, and again, by the way, most of my talk, I will try to be more general for object storage. I don't want this to make this a Azure Blob Storage talk, but that probably won't be interesting to a whole bunch of you. It's more interesting if you kind of talk in general terms about object storage systems. So even though I may say Blob or Azure, I'll call out where things were very specific to Azure Blob versus kind of applying to most hyperscaler object storage out there. But naturally, I'll talk about this through the lens of our experiences at the time. And what we looked at was, hey, first, how are we going to start servicing these throughput requests, which definitely could kind of push us over the limits into throttling and things like that. And the second thing we started looking at was how do we start to think about larger scale, right? Larger, not just capacity scale, which is the only challenge until then, but larger throughput scale, larger TPS scale. So those are things that we looked at. The other things that were happening in this time period, which this one is specific to Azure Blob Storage, is we looked at how to support things in the Hadoop ecosystem, HDFS file systems, like directory renames, right, and ACLs and things like that, which were certainly not something object storage systems could handle until then. Pretty typically a rename, it's a key value, right? There's no directory structure, it's just implied with the slashes and other things. And so a rename of a directory somewhere in the hierarchy meant you were pretty much copying all the blobs over, or doing something underneath the covers that wasn't rename. So we built a indirection layer that we call the hierarchical namespace, the marketing name for it was Azure Data Lake Storage. But we built this hierarchical namespace layer that kept all the flat namespace and all of that, the key value store underneath intact, but layered on this namespace concept. There's other object storage systems that more recently caught up, I'd say in the last year or two, are also experimenting with this, so that's another trend that you can look at. But then what's happened, I think, in the last few years is the following, right? First of all, by the way, very interesting in development that I don't think I would have foreseen is there are now a number of what I call pure play cloud storage services out there, right? There's Wasabi, there's Backblaze's B2, there's Cloudflare's R2, all very credible, all S3 compatible cloud storage systems that don't really have an ecosystem of computation or other PaaS services around them. So that's something that's happened as a sidebar from the, not just the hyperscalers having cloud object storage. But if you look at those two developments down below, the other thing that's happened, I would say, maybe last 4 years, 5 years, is the consideration to use object storage for HPC workloads, right? And not just as an HPC archive, like throw our old data over the wall and never access it, but actually like, hey, can we actually use this for throughput-driven workloads? Can we use this for sequential workloads or scanning through a bunch of objects? And those folks had lots of legacy code and wanted POSIX access to their data, preferably. To this day, if you look at most of the large supercomputers and the large national labs, they're very interested in the scale and the TCO benefits of object storage, but they haven't rewritten their applications. That'll probably take another decade or two to get there. So that's one of the things that had come up. And different hyperscalers have approached this in different ways. We launched support for NFS v3 on top of object storage back in 2021, kind of looking at that trend. Not the most performant thing, but definitely great for compatibility. And then we've also invested, as have the other cloud hyperscalers, in having fuse drivers. So you can kind of abstract all of the REST API communication and just have a mount point for code that talks to these things. So that, and the reason I'm kind of stressing that is that I think directly led to where we are today with AI and object storage, because AI training is just a special case of HPC, right? Like, people said, hey, we have GPUs, we're still running these computational jobs just on the GPUs instead of CPUs. And they started using object storage, and because they weren't necessarily burdened by the legacy of the HPC code and the HPC, they were willing to go write their code from scratch. They were already rewriting all of their CPU code, so they were able to use our latest APIs, build little tools and other things on top of it. And really, I think, even though they were doing, executing an HPC workload, they were really leveraging object storage to its fullest extent. And we saw this, we were fortunate, as folks know now publicly, to have OpenAI sort of leading the way with us and sort of working with us to push our platform and help teach us about these things. So that was an interesting kind of evolution. We actually have a talk tomorrow at 2:30. My colleagues Jason and Jagan here will be talking a lot more about how OpenAI really pushed our platform and what we did in response. If that's an interesting topic to you from a systems perspective, I believe it's tomorrow at 2:30 to 3:20. So I won't talk too much more about AI training since they'll go into it quite a bit. But that then led, okay, well, you're already using it for AI training. Why not use it for AI inferencing? Why not go build ChatGPT on top of Azure Blob Storage and all of the other chat applications and AI applications and all the other clouds as well? So that kind of brings us to the current day where we have a pretty heavy usage of object storage on any cloud platform for both training and fine-tuning, which are more traditional HPC workloads, and inferencing, which is not at all a traditional HPC workload, but it kind of went along with the flow. So that's anyway a little bit of an arc. I thought it was interesting to kind of consider why and how we've come here over the years, starting with what was essentially kind of considered settled canon, right? Like object storage was supposed to be this very boring thing. It's key, you provide a key, you store an object, it reliably returns it to you. Everybody's happy. Nobody cares about latency. Nobody cares about performance. It was supposed to be the most boring thing on the planet in the mid-2015s, 2020, and all of a sudden over the last few years has gotten a lot more interesting. And for all of you, as I was saying earlier, we're all storage geeks. As systems engineers, this is absolutely fascinating and awesome to see because it presents all these crazy problems that a lot of really smart engineers that I'm privileged to speak for at this conference, back home or back in many offices around the world now, have spent years kind of working on and scaling our systems and designing our systems. And this is the kind of stuff that I think a lot of us live for. It's fun. So anyway, with all of that history, let's get into what's actually happening with AI workloads and storage requirements and things like that. So I want to talk a little bit about what's happening with the typical AI pipeline. Being a storage thing, we'll take a storage-centric view. Of course, storage people like to say storage is the center of everything, right? So you start, but this essentially is true if you're looking at what's happening here. You're looking at the left side, it's about training, and then the right side is about inferencing. But you start with bringing data in. You need raw data sets. You need data acquisition. You need to clean that data. You need to dedupe it. You need to annotate it. You need to do all these steps where you're still, again, working with large amounts of raw, unstructured data. When we're dealing with textual models, this data wasn't that big. Now with multimodal models, you're talking about humongous amounts of images and video data that has to go through the same pipeline. And really kind of, again, is stressing our systems in ways that it wasn't true even a year or two ago. Once all of that data is cleaned and prepared, you have this sort of packaged training data that can actually be fed to the GPUs for training. Training as a side effect also generates these checkpoints that can be very large and grow with model complexity. So that's another interesting challenge of just dealing with, your GPUs are blocked. It's kind of a barrier function until you write all of your checkpoints, your GPUs can't go forward. And if you have a failure and you have to restore, you actually have to wait for the system to load the checkpoint throughout the cluster. So you can imagine this is a bottleneck, and there's a whole bunch of interesting work that's been done, again, not necessarily specific to Azure, around node local caching and things like that to compensate for the fact that you're necessarily dealing with disaggregated remote storage. So all of that happens. You have these checkpoints, you have these models that you're ready to go with. You then have to take these base models and distribute them to wherever the inferencing is happening. So there's a little bit of a distribution problem there, much easier to handle in some sense in the front end of the pipe. Lots of people don't do training. Like very few people today are training foundation models, and we expect that'll continue. The amount of resources necessary to train a foundation model is, in dollar terms, now probably well into the hundreds of millions, and maybe in the billions, to kind of get everything, running to have a big family of foundation models. But lots of people do fine-tuning of data. They bring their domain-specific data. They bring their proprietary or private enterprise data and want to train. So you might, be training a model for healthcare. You might be training it for legal services and other things. And you bring that data. It's pretty much the same pipeline, so I'm not going to repeat all of that, but it really kind of combines, takes the base model weights, runs a training job, adjusts the model weights, and now you're using this fine-tuned model to run your inferencing and run your AI applications. So you kind of put that all together. Let's talk a little bit about what are the requirements for storage on these things. On the left side, the training and fine-tuning, I think really first, again, this says Azure, but you can kind of look at it as any cloud. Bringing the raw training data, just ingesting it from wherever it is. It might be on premises, it might be coming in from these hybrid data sources where the data is being collected, let's say a manufacturing floor or something like that. The preparation of data looks a lot like analytics preparation jobs, right? You're dealing often with the same kind of tools. So Spark clusters, Databricks clusters, et cetera. Then you do the training where those GPUs are reading your training data. And lastly, you do still have to worry about sort of the nuts and bolts. Data management, being able to do effective lifecycle management, help people understand what the cost of this data is. One of the things we're running into right now is when people talk about responsible AI, there's a big component of storage in there because you have to keep the raw data, you have to keep some sense of lineage and provenance. Again, in terms of like we've heard of storage people, and it's like, oh, that's interesting that's come up again, where people need to keep an idea, they need to tag the data, they need to say, hey, this model was trained with what data set, right? And be able to prove that if there's any issues of bias or hallucination or things like that. So there is some interesting thinking about how much data do we keep, what about the models and the checkpoints from the training runs, how do we keep that, what can we get rid of? So those are kind of still, I would say, current challenges folks are dealing with. On the deployment and inference side, like I said, model distribution load times matter, and you still care a bit about data management. So this is what the landscape looks like now. And before we dive into the RAG pattern and do a little, kind of talk through some demos and some things here, let's spend a little bit of time just setting the stage for some of the storage services. I'm going to assume not everybody's necessarily familiar with Azure Storage, so I'll just briefly show what we're talking about here. It's not dissimilar from other cloud storage platforms. We have a block set of services, block storage. We have a file storage set of services, and we have object storage. Most of this talk, I'm talking about object storage as the canonical set. As you see, there's the Azure Blob, which is our flat namespace term, if you will. And you can turn on the namespace, even though it's called a different thing. Data lake storage is really just a config switch to turn on that hierarchical namespace. We'll talk a little bit about what's called premium blob storage, which is SSD-backed object storage. That has proven to be very interesting in the AI space, as we've been discovering ourselves. And I talked a little bit in that first slide about hierarchical namespace, but I will show this from that perspective of, this architecture has allowed us, we built it for analytics. We didn't build it, kind of presupposing anything AI. But it was very much a requirement for analytics, and we built this thing, and it's become very useful for us, even with data for training and other things that are used. So the whole data preparation pipeline, having the ability to have that hierarchical namespace is interesting. So with that, let me turn it over to Saurabh, who's going to walk you through the meat of the talk, if you will, with RAG and the RAG pipelines and how you use object storage there and what we've learned there.
Thank you, Vamshi. Am I audible at the back? Is it all good? All right. Let's dive into RAG, retrieval augmented generation with object storage. And I think Vamshi talked about the idea of fine-tuning being the way that enterprises can actually get their own custom data and make these models work with their own data to be able to reason, to be able to provide responses. But fine-tuning is not the only way. It's, of course, I think, Vamshi, you said billions of dollars, perhaps hundreds of millions. But there is actually a much cheaper mechanism to get that to happen. And this slide essentially talks about those three modalities of doing that. So from left to right, the first one is prompt engineering, where you have these context windows that these LLMs have that can accept text, it can accept images and videos. The idea is you provide your own data, your own proprietary knowledge base as part of the prompt that goes into the LLM. And so the LLM is not really learning anything. It's leveraging the same prompt, the same context, to reason better on the question that you provided to it. So we call this in-context learning. The second part to that is fine-tuning, where you essentially update the model's weights. Think of this similar to learning new skills. I don't know how to play the guitar, but if I practice with the guitar, perhaps my brain is going to get rewired. And the next time I'm playing a chord, I can actually then go to the chord without thinking much about it. So that's learning new skills, and that's fine-tuning. The last one, which is retrieval augmented generation, is essentially learning new facts. I think of it as, if somebody asks me a question, let's say about Ocean Store, and I don't know anything about Ocean Store, I'll go look up the PDF, and I'll find the relevant information that is relevant to the question, retrieve that information, and try to see if I can answer the question about Ocean Store. So that's essentially learning new facts. Now, there is an aspect of retrieval involved which combines reasoning and knowledge together. So you have the internal knowledge or the internal foundation skills that an LLM has. You take that, you augment that set of weights with external knowledge, and then you augment that knowledge to the prompt so that the LLM can reason better. And that's why we call retrieval augmented generation as a way to combine reasoning and knowledge. So with that context, let's look at what would be the canonical picture of a RAG pipeline from a storage perspective. And the RAG pipeline has two primary sections. The first one is the preparation, where you ingest data. This is similar to how you do AI training or fine-tuning. So you ingest your data. You also clean your data. You pre-process it. But the uniqueness about retrieval augmented generation is breaking down that data set into small chunks. And for all our storage geeks, this is basically small objects, small files. And you break these chunks down from your original data source because, let's face it, these LLMs have context windows which are finites. Those tokens cost money. We want to make sure we get high quality, rich information from our knowledge base that is most relevant to the query that is provided. And that's why we break it down into chunks, right? And so that those chunks get stored also on object storage. And then from there, we convert these chunks into what we call vectors. And this is where an embedding model comes in, which does the embedding generation. And the reason we do that is quite simple. Every LLM has three parts. It has a query engine, it has a key engine, and it has an embedding engine. The embedding engine is what assigns meaning, semantic meaning, to whatever data is provided to the LLM. And so you cannot just provide text or images to the LLM and expect that it is going to understand everything. You need to convert it to embeddings that the LLM understands in terms of meaning. And so that embedding generation is a core step of this preparation for the RAG pipeline. These embeddings then go into a vector database. And this is not a NoSQL or a SQL structured database. This is a database to store vectors, tuples of numbers together that represent context. When a query comes in, we essentially perform a vector similarity search. And so this is the, I love linear algebra, and this is basically finding cosine similarity between two vectors to see how close they are in the vector of field representation of that context. And then based on that, we get the relevant high quality chunks, augment our prompt with it, which is the prompt augmentation section here. This is where you're retrieving data from the object storage layer. And then finally, you perform inference by essentially sending that data to the LLM. So there is a lot of interaction, as you can see, that is happening with the unstructured data storage layer down below, which, by the way, also motivates some of the very important storage requirements that emerge from this pipeline. The first thing, we need to make sure enterprises, wherever they are, can easily bring massive amounts of data, which they have in their corpus, perhaps NAS devices, different cloud storage layers, into the object storage layer. So you need a strong ingestion engine. The second thing is you need low latency access. Imagine you send a query, and now you're waiting because the object storage layer underneath is not able to serve the query with the relevant number of chunks in the relevant amount of time. And that can essentially spoil the user experience. So you need low latency access. Of course, you need integration with vector DB functionality, because at the end of the day, these chunks and the embeddings that we talked about are very closely related. And so if you're not talking to the vector DB, you'll not be able to figure out which chunk you should be retrieving based on the embedding that is relevant to the query. The fourth thing here is one of the most important thing for enterprises. This is something which everybody worries about. What if I ask a question and I get a response that does not mirror the actual state of my knowledge base? That's why freshness of the data and reflecting that freshness in the query for retrieval augmented generation is such an important factor. We'll talk about some of the integrations that object storage systems today have to enable timely updates of the vector index so that the query always presents fresh information as a response. And finally, and most importantly, this is super important from the perspective of data security and data governance. Vamshi was talking about audits and data lineage. Data governance is very important. You want to make sure just the right amount of information is presented to the user that has access to that information. And so you do not want unintended data to be accessed by a user that does not have access to it. Therefore, security and access control of this data is super important as well. So with that frame, we'll talk about some of the things that object storage enables today. Of course, we are taking some of the examples of what Azure Blob Storage offers. The first pillar is multi-protocol access. You need to have the ability or the compatibility with different storage systems, different applications, to bring in heterogeneous data into object storage for this pipeline that I just talked about. The second, for low latency access, there is SSD-backed storage systems which are becoming more and more prevalent, and they're enabling technologies for blob storage, for example, Premium Blob that is built on SSD-backed storage to enable low latency access. We also integrate, by the way, with all the vector DBs, and this is true for most object storage systems today. So whether it's Pinecone, whether it's Azure AI Search, these vector DBs become front and center in this RAG pipeline, and the integration with object storage is super important there. For freshness, we have a unique feature which we call blob change feed, which I'll show the demo for in a bit, and change notifications, which enable on-demand updation of the index. And finally, for security, we integrate with Azure Active Directory. It could be any identity-based system that offers RBAC. And additionally, for blob storage, we have ABAC or attribute-based access control. Okay, so with that, let's dive into our demo. And I'll switch a couple of screens here. So if something breaks, my apologies for that, but hopefully not. Let's see. Okay, this doesn't show the demo screen. Interesting. I think I need to escape and then. I don't see it on that screen. So let's see if I can extend it. Yeah, I'm just doing that. Yeah, there you go. Okay, try again. Okay. Did it? Okay, let me just try again if it works. Nope. It's not working. Yeah. Yeah, let me see if I can do that. Let me do that screen only, and then that should work. Let's try again.
Well, for the first time on a screen.
Now let's try, and this is going to be hard, by the way, because I'll have to look at this screen and try this out. Please bear with me, folks. Okay, we are online, I think, and it'll be a bit harder for me to navigate things. So if I click on something that I don't intend to click on, please let me know. Okay, all right. Okay, this is just to help me here. Okay, so what I've done is I've basically hooked up a sample RAG application here. And I'm going to sort of fix my mic a bit so I can see the screen. But what this RAG application is essentially doing is it has a corpus of PDF files that are stored inside a blob storage account. There are thousands of PDFs here. And what we're going to do is we're going to try and look at a setup that hooks up LangChain and Pinecone together. And we are going to perform retrieval augmented generation with that corpus of data. And while I do that, maybe what will help me is to go back to my deck here and just show a quick roundup of what we are doing with our demo here. So this is what is happening here. We have LangChain as the orchestrator, which is essentially doing the data prep. Okay, let's see if I can go PowerPoint. There we go. LangChain as a data preparation orchestrator. We have Pinecone as the vector database that is performing the similarity search and giving us all the vectors and the chunks that are needed for performing RAG. And backing all of this is OpenAI GPT-4o and embedding models associated with that. So we'll go back to the demo again. And hopefully this time we're going to be able to see everything working. Okay, so let's query. Let's query without any context, what is grit in AI? So it gives me an English definition of grit, which again, and it tries to do something interesting. It says, for AI, you can, it could mean this and it could mean that. But it's actually more complicated than that. Grit actually does have a meaning. So this time what we're going to do is we're going to query this with the context. What is grit in AI? And this time, it gives me a better definition. It tells me grit stands for generative representational instruction tuning. And it also tells me which references it is getting all of this information from. So I actually have this reference downloaded. I believe, if not, let me open it. It's a little hard to see from here, so bear with me on that. There we go. Open the file, there you go. So it actually pulls this information from this PDF. What I will do now is to go back to the piece of code that I showed and talk about which sections are we really sort of working with to make that application possible. So there are various sections here. The first portion is to essentially, of course, generate the response. But the main thing that is happening here is we are essentially processing a bunch of PDF chunks. And the way we are doing that is in this piece of code here. We are using a bunch of text splitters to be able to do that. And the text splitters are coming from LangChain, that is breaking down the PDF into smaller chunks. And those chunks are essentially what is sent to the vector database to essentially get the vectors and then index those vectors and upsert them into Pinecone. And so that is happening. So this is generate embeddings. I need to be able to go here. All right, so this is the place where I'm processing all my PDFs. And this is getting the list of updated and deleted blobs as well. And finally, this is where I'm breaking it down into chunks using LangChain's character text splitter, and then returning back those PDF chunks. These chunks are then retrieved as part of my generate response. And so this is the place where I'm generating the embeddings, as you can see here. And this is what essentially enables this response to be shown at the bottom here. Now I'm going to do something interesting. And what I'm going to do here is I'm going to go and delete this particular file from the knowledge base. Oh, one second. All of them look the same, so So this is my PDF. I'm going to go and delete this PDF. Am I on the delete button here? This one? OK, thank you. All right. So now I've successfully deleted this blob. And now if I were to go back to that same query and run that same query again, we expect that query should get updated, right? So what we're going to do here is we're going to go back. And as a result of all of these changes, what might end up happening is you would need to process and generate those chunks again, because now the vector DB needs to be updated. And so for that, I'm going to run a function called process PDFs. And hopefully, in a couple of minutes, it is going to be able to determine what changed in the process and therefore update those indexes. While that is happening, let me actually talk about what I'm going to do behind the scenes to be able to enable this process. All right. So now what we're looking at here is the feature called change feed, where I'm trying to get the change feed to list all the changes between a start time and an end time. And this is extremely useful because mostly what happens is when you look at change notifications, it's an on-demand thing. The moment it happens, you can re-trigger the index. But what if you want to process these changes as a batch at the end of the day, and therefore you need an ordered and guaranteed and consistent set of changes? That is exactly what change feed offers. And what it does is it gives you this consistent and guaranteed log of changes in order so you can process them for situations like this. So let's say something gets updated, deleted, you can process those changes in order and update your vectors as you need to update them, right? So typically what happens is when there are so many parallel updates happening, we take a bit of time, but we ensure that all those changes are ordered and consistent. We're going to try this again. Process PDFs. And this time, it actually found the deleted PDF. And all these were the chunks which were essentially stored on object storage, right? So it deleted those chunks. And by the way, it also deleted the vectors from Pinecone. You can see all these vector representations are coming from the chunk IDs which were stored inside of Pinecone, right? So now I'll do this again. I'll run my query again, and hopefully I'll get an updated response. query what is grid in AI. And there you go. This time it's changed. And now you only see, let me actually move this up so it's visible to everybody at the back as well. But this time you see only one reference. And as you can see, the response also has been updated. It doesn't show anymore the generative representational instruction tuning. And this update essentially shows that you can do this very, very easily with blob storage and Pinecone. OK, I'll go back to the deck here. I'll not go through the process because this is essentially what we just showed. We are taking change feed, putting into LangChain, getting the embeddings. And then finally, when the user prompt comes in, we do a similarity search, retrieve all the chunks, and finally generate the response. OK, so all of this that was happening was actually running on top of premium blob storage, which is SSD-backed. And SSD-backed storage has the advantage that it can actually give you consistent low latency, high IOPS, very high throughput, and can maintain that performance with sustained load. And this has enabled some very interesting applications from the perspective of not just AI, but if you look at data hydration for ingestion, whether it's data processing pipelines, integration with analytic engines, real-time streaming analytics, or even artificial intelligence or machine learning, SSD-backed storage gives you the ability to get that consistent low latency performance that is demanded of object storage for these applications. Well, this is just a comparison to say, how did premium blob do against standard blob, which is HDD based? And overall, what happens is we see premium blob, which is SSD backed, delivers 3x faster performance. And because we are able to essentially, get much higher IOPS for the same hardware, we pass on those savings in terms of hardware back to our customers. And you also get 65% savings in terms of transaction costs. All right, so now, going back to what we talked about in the beginning of the presentation, today in the present, object storage is powering AI pipelines and vector DBs. That's a huge change from where we started. And this essentially comes from a couple of key advancements that have happened. We are able to now disaggregate and scale out storage across various clusters and then provide that scaled out capacity in a single standard account, which might even be backed by HDD. So what you see on the right here is what we call Azure Blob Storage Scale Account, which can actually do more than tens of TBPS of throughput with just a single storage account. And we essentially distribute the IOs to different clusters so that you're never bottlenecked in terms of throughput. So this kind of a scaling out of storage is a pattern that we see a lot, and that is something that delivers great performance. Vamshi, of course, talked about GPU node local access and caching. There is a bunch of analytics engine integration and protocol access that enables the ability to have those kind of processing pipelines where you can use tools like Spark, Hadoop, Databricks to be able to perform multiple kinds of data pre-processing before you push this data into LLMs. This is the interesting one, which is vector DBs. Now, you might think that vector DBs have indexes and they need to be stored on really performant flash storage. Well, it turns out if you do that, you need to scale up compute and storage a lot, and that doesn't work when you have very large petabyte scale data corpuses, and you need to index them at scale and also maintain freshness. So one of the implementations that Pinecone, in fact, did was to essentially get to separate out storage and compute, but then store the index of the data corpus on object storage. And so they have these two kind of pipelines, and these pipelines enable not just freshness, but ensure that consistently the index stays up to date for a large corpus of data that is stored on the object storage platform. So this is something which is enabled by object storage as well. And as I showed, change feed and change notifications deliver freshness for these kind of applications. All right, now I'll hand it over to Vamshi to talk about the fun, cool thing of LLM OS, which was coined by Andrej Karpathy, and what can object storage do in that future of LLM OS. Vamshi?
Thanks, Saurabh. All right, start wrapping up here. But as you saw from Saurabh, and by the way, good job. I don't think I could have done this sideways demoing that you were doing. But that's awesome. So that's all today, right? All the things that you saw, all of the things that Saurabh showed you is possible today with object storage systems. And it's really things that our customers are doing on our platform today. So when we look to what's coming next, I think that's kind of an interesting thing to contemplate here. And as Saurabh said, Andrej Karpathy is a well-known ML researcher. Great videos explaining all this stuff, by the way. So if you're looking for an explainer, go look up his YouTube channel. Wonderful content. But one of the things he talked about in one of his videos was this notion about LLMs evolving into this LLM operating system and being able to kind of run these sort of agent workflows and be able to read and learn and understand things. He kind of draws that analogy to an operating system. And of course, an operating system needs a file system. And I think when we think about that and what we will need, we'll continue to need scalable access to many, many petabytes or exabytes of data, right? We'll continue to have this notion of retrieval and handling of multi-modal unstructured data. So it's not just PDFs and text data like Saurabh showed, but imagine this happening with image data or video data at scale. Let's say, manufacturing images from a factory floor or video from, monitoring of an area or something like that. That's a lot of data to kind of process and be able to use in these RAG pipelines. And the last piece here is this notion of having system context or user context. As these systems get more and more interesting, and you see this today, by the way, if you're using ChatGPT, unless you opt out or delete the history, it retains all of the history and the context of what you've asked it before, and it is using that to answer you better, right? And you can actually kind of go configure a bunch of stuff. All of that also needs to get stored somewhere, and the kinds of data that will be stored will get increasingly more complex over time. We do believe that object storage will continue to meet these needs in the future, right? Today, object storage is already at exabyte scale capacity on most hyperscaler platforms. We're able to do terabits of throughput, able to do millions of IOPS, and those needs will continue to grow, and we'll have to keep our systems in line with those requirements. We talked a bunch about SSD-backed performance storage. Again, 5 years ago, nobody would have thought object storage on SSDs was an interesting thing. It's like those are fundamentally not the right thing to think about together, but turns out they're interesting. Kind of almost by accident, we launched object storage on Azure Premium Blob Storage 5 years ago now. I think it came out in 2019, June. And we launched it for interactive scenarios. Again, nothing to do with AI, but it's helping us quite a lot here. Indexing is another thing. Not only do you have these vector databases and indexes, but having some kind of tag-based or metadata-based indexing and search on the underlying object storage system, I think will increasingly become interesting and important. And then the last piece, security and making sure this user context, as you store more and more user context, you really need it to be protected and protected well, because there's a lot of, we're going to end up trusting these systems a ton, just like, you have all the stuff on, that you've already kind of given up on your machine and systems. Imagine these systems knowing a lot more about us. So security, identity-based security, making sure you have sort of policy-based management and all that becomes very, very important. I think those are things that we're going to have to build. I'm not saying that, or at least certainly Azure's object storage system doesn't do all of these things yet, and those are things that we're working on. So let me wrap up here by saying a couple of things. First, object storage has proven to be pretty ideal for AI training and fine-tuning. Again, a quick plug for tomorrow's talk. I think if you want to have these real-world kind of conversation from what OpenAI did on top of our systems, Jason's been working with them for a long time. Jagan, who's the other speaker, has been working on object storage systems for well over a decade now, so you can have a great conversation tomorrow as well. They're both here, by the way, so if you want to grab them after the talk, you can. So come to that talk for more detail on that left side. But today we spent quite a bit of time talking about RAG-based LLM apps and how there's sort of this real-world usage of object storage. Interesting challenges and problems for all of us to take away and think about how these things are going to continue to evolve in the future. So that's all I had. Thank you so much for coming. We'll be here for a while and ask any questions. Thanks again. Happy to take questions. If folks want to head out and get a beer or something, please feel free. But please go ahead. Yeah.
How much of your training and inference applications leveraging object store, and how much percentage are still asking for POSIX kind of at a high level?
Yeah.
What are you seeing? Which directions you want to be investing more?
Yeah.
Object or POSIX?
Yeah, let me repeat the question. So the question was, how much do we see training and other things leveraging object storage versus still looking for POSIX type semantics? So interestingly, that distinction has, I think, on every platform, every hyperscaler platform today been addressed through a Fuse driver, right? So everybody provides, we have something called Blob Fuse 2. So you can mount an object storage account, an entire petabyte scale account or whatever, as a mount point on your Linux VM. So you get not quite full POSIX functionality, but POSIX-like functionality. So even if you're doing things that are just like your normal, like I'm treating this like a mount point, I'm manipulating the data, it works today with object storage. So a lot of these training folks, they aren't necessarily changing their code. Sometimes some of them, of course, are using our tools or building tools to go fetch the data through the REST API to the local node. But they're also doing these kinds of things where they're just mounting the entire data estate as a mount point. So I think you're kind of getting the best of both worlds today. There's a lot of stuff that happens underneath the covers with those. BlobFuse 2 is an open source project, so you're welcome to kind of go check out the code and see what we do and don't do in terms of caching and other things to keep things performant despite that. Yeah, thanks. Good question. Go ahead, please.
You mentioned about vector databases. You mentioned indices or indexes.
Mm-hmm.
Putting the indexes in storage. So naturally, the size of the index or the corpus of say a terabyte is. Can you comment on the corpus versus how big the index actually ended up becoming?
Great question. So the question is vector databases, indexes, how big is the index versus the corpus? Yeah, this is a little bit out of my domain knowledge, but I'll comment on it from what I know from other folks who work on this problem space. This is an interesting problem because the indexes are quite big, actually, relative to the corpus size. And I think this is one of the challenges folks are struggling with. You can have a terabyte of data, and you can have a terabyte or more of indexes to go with that. And historically, you keep these indexes in memory. This is why vector databases are so ridiculously expensive. You go look up cost for those things. They're just crazy expensive, at least for all of us storage people who are used to selling stuff for pennies. So that's where I think this trade-off is coming, where they're saying, hey, can we offload the non-hot indexes to object storage and get them just in time? That makes a huge difference to how much more they can index. Most of the people that you see today, like doing this kind of data corpus indexing into vector databases, are very nervous because of cost of the vector index in building bigger corpuses. All the AI applications, we see like people go 10 terabytes, 50 terabytes, that's a big corpus. And we're like, come on, you have like 20 petabytes of data. Don't you want to like go index all of that and be able to go to thing? And the systems aren't quite there yet. So I think that's a place where you're going to get a lot better. It's not just vector databases and similarity searches, by the way. There's also all of this research, and this is where I said it's out of my domain area, where people are doing these hybrid ranking systems. So hybrid search, they combine vector searches with full text search, with other kinds of search, and they build these hybrid searches and hybrid rankers. So they're trying to cut down on those indexes and the need for those vector indexes by combining with other kind of things. So there's some talks, at least again, I'll use the Microsoft reference here, but I'm sure there's other research talks out there. Azure AI Search has done a bunch of, had a bunch of conversations about this. A gentleman named Pablo Castro, if you search for him, he's done a couple of talks even in the last year talking about these challenges with the indexes and ranking. But great question, thanks. Any other questions? Cool, go ahead.
Are your customers also putting checkpoints on your blob premium, or using the local instance and then?
Yeah, great question. Yeah, the question is, are customers putting these checkpoints on blob storage, maybe even premium blob storage, or are they using local NVMe and other things? So yes, they're very much doing this sort of tiered caching thing. So if the GPU has the local NVMe, that's the fastest thing, right? So you definitely want to keep a cache there, and then if you can restore from there, great. But you do every n checkpoints or so persist out to object storage. Again, the way I understand this happening, and you'll hear more about this tomorrow, is if the kind of failure mode of these GPU nodes is such that you don't have the right shards to reload, because it's even if it's a distributed cache across these things, and some of the AI training folks are doing distributed caches, not just node local. They're building a fabric across all of the GPU nodes and reading. If you lose enough nodes, though, you have to end up faulting back out to blob storage. But yes, to your point, you need to keep those GPUs fed and not idle. So if you can get it locally and on an InfiniBand network off of the GPU nodes, you absolutely want to do that. And that's kind of what the way we are thinking about building these caching layers is. Yeah, nothing changed that on the spatial locality concept, right? Yeah, absolutely. Right. Any other questions, folks? Yeah, again, we're here. Please find us in the hallway. If the Microsoft folks want to raise their hands here, that way people know they can come find you. But yeah, please come talk to us. Thanks again.
Thank you.